My name is J-Ro, and I'll be presenting Communication-Efficient Agnostic Federated Averaging. This was worked on in collaboration with some of my collaborators from Google, including Mingqing Chen, Rajiv Mathews, Mehryar Mohri, and Ananda Theertha Suresh. Before we get started, I want to give a brief introduction and background into federated learning. So federated learning is a machine learning technique that trains a single algorithm across decentralized examples. And in federated learning, there are typically two main actors. There's the client and the server. Now, the clients are typically a multitude and distributed, and the decentralized examples are each client's local examples data set, whereas the server is one centralized server that does aggregation. And so typically you think of two types of and two settings for federated learning. One is cross-silo, where clients are organizations such as banks or hospitals, and the other is cross-device, where clients could be something like edge devices or smartphones. So one very common example given for federated learning is training, for example, a single shared language model on multiple client devices or multiple client mobile phones or smartphones. And so in the figure below, we go through a typical setup for a federated learning algorithm. So in step one, the server initializes the shared model. This could be warm started, or it could also just be a completely new initialization. But it's the same model, and it's only on the centralized server, so a single server. Then in step two, the server samples some subset of the clients and sends the shared model to each of them, or the initialized model to each of the sampled clients. Now in step three, those same clients do multiple steps of local training on their local training data sets. So each of the clients that were sampled and participating in training will have slightly different models depending on what their local data set was. Finally, in step four, the clients send back the updated models back to the server, and the server does some method of aggregation so that all of these multiple client updates are aggregated into a single update on the server. And once the update is done, the server again has a single shared model and repeats back to step one with the new model update. Now, given the setup and background into federated learning, I wanted to get into some of the motivations behind why we were looking at the agnostic federated averaging algorithm. So in federated training, algorithms can be potentially biased towards different clients because the standard learning objective minimizes loss with respect to the uniform distribution. But in federated learning, this distribution can actually differ between training time and inference time just because of the nature of the problem, where we're sampling some subset of clients at different times of the day, for example. Now, previously, agnostic federated learning, there was an agnostic federated learning algorithm that was proposed for only the cross-silo setting. So the cross-silo setting, like I mentioned before, could be for banks or hospitals, and the clients are organizations, so they're much larger and much fewer. So the number of clients is very small. But this did not work and did not apply well to the cross-device setting, where there are potentially millions of clients. So as you can imagine, for example, with mobile phones, you could imagine that there are hundreds of millions of mobile phones out there, each with their own local data sets for each client or for each user in that case. So our goal was to come up with a communication efficient variant of the agnostic algorithm that minimizes the domain agnostic objective. And we also wanted it to be amenable to privacy preserving techniques such as secure aggregation. So when we were doing this problem, we found that there were essentially two types of domains that were naturally occurring in the federated learning setting or environment. The first is what we call data partition, where each client has data from one or more domains. And so in this case, domains represent different types of data. One example of this could be, for example, on your mobile phone, you can have the same user typing for different applications. So there could be Gmail, there could be Messenger, and there could also be something like Google search or web search. And so in that case, you have a single client, but with data from multiple domains, which in that case is the application. And the second type of partition we call client partition, where each client has data from exactly one domain. And so in this case, domains represent clusters of clients. And one very easy parallel for this could be, for example, geolocation. So clients that are located in the US will only have data for that location, whereas clients located in, for example, Mexico will have, their data set would only be data for that locale as well, geolocation. And later on in our experiments, we'll show two actual experiments for each of these types of partitions and show that our agnostic algorithm performs well on both types. So in explaining the main algorithm, we wanted to highlight a couple of things about the agnostic federated averaging algorithm. The 3 key points is that each round of federated learning for this algorithm uses only a single round of transmission, meaning there's only one round of communication from server to client and client to server. So this is similar to federated averaging. The second is that clients train with multiple steps of local SGD, also similar to federated averaging. And so in this case, this would correspond to step 3 in the original figure, the first figure. Finally, the third point that we want to mention is that the server will never have access to the individual client data, but only aggregated statistics. So this will actually make it compatible and amenable to secure aggregation. So the server will never be able to see an individual client's statistics or data, but only see the aggregate across all clients that were sampled for that training round. In algorithm 1, we lay out the steps for the agnostic federated averaging algorithm. I won't go into too much detail here, but you can reference back to the paper for additional details that I might not cover. But essentially what's happening is that for each round of training for federated training, for each of those clients in the sample, we do local steps of SGD while also keeping track of domain statistics. In this case, we're keeping track of the loss per domain as well as the number of examples per domain. We send back those domain statistics along with the client model updates as part of the client update function. And in this step here, we're aggregating both the client model updates as well as the domain statistics. So this would be what we mentioned in the third point, where we're aggregating across clients and never seeing the actual specific or individual client statistics for each domain. So at the end of it, essentially, we'll see the total loss per domain across all clients, as well as the total number of examples per domain across all clients, which we'll then use to update the model as well as our domain weights. And we go into much more formal detail in the paper with the formulation as well as some basic proofs, but we choose to just move on to the experiments for the purposes of this poster. So one thing that we mentioned was that this was a communication efficient variant of the original agnostic algorithm. So one thing that might be helpful is to actually evaluate the communication cost and compare it to our baseline, which in this case is federated averaging, to see how much more communication cost there is or how much less. So in this table on the bottom, we compare federated averaging to agnostic and look at the number of parameters that are essentially communicated per round. So the two, we multiply by 2 to indicate both sending from client to server, or sorry, sending from server to client and sending back from client to server. But C is the number of clients sampled per round, and this next term essentially tells you the number of parameters in our model. So it's the same. Agnostic has the same number of parameters per round with this small additional addition, which is essentially going to represent the domain statistics that we mentioned before, the domain loss and the domain number of examples. And this is a very small offset, or in addition to the original model parameters, given that P is much smaller than the number of model parameters. So actually, this additional cost is quite small and is a very small overhead. And we found in practice that the agnostic algorithm actually can converge in fewer communication rounds than federated averaging. So that almost also effectively eliminates this additional offset and actually might result in, over the course of total communication rounds, less number of parameters required compared to federated averaging. So finally, we'll go into our experiments and results. So in all of our experiments, we're comparing 3 algorithms. The first is federated averaging uniform. This is essentially the vanilla federated averaging with trained uniformly on all available data. So there's no concept of domain during training here. We just treat all data the same. There's federated averaging that's target only. In this case, we filter out the data such that we're only training on the target domain, and we only train using federated averaging on the target domain. And the third algorithm is going to be our agnostic federated averaging algorithm. In this case, we train on all available data, but this time we take note of and actually use domain and keep track of domain during training. So we ran 2 types of language modeling experiments. The first is Stack Overflow. This is a simulation experiment based on the Stack Overflow dataset. And for a bit of background, this dataset is essentially questions and answers from the public Stack Overflow forum, and it's grouped by username or Stack Overflow username. So that means that we can group questions and answers by the original poster, and that's what makes this a federated dataset. In this case, or in this simulation, there are essentially 2 types of domains. One is questions and the other is answers. And in this case, it's a data partition because users can post both questions as well as answers. In the table below, you'll see performance as well as difference two measures here. And the second is accuracy and vocab. And we define it more concretely in the paper, but essentially accuracy and vocab allows us to make valid comparisons across different models with different vocabulary sizes. You'll notice that the agnostic algorithm performs the best on the answer domain, while also decreasing the difference between answers and questions. So in this Stack Overflow example, in the 2 domains, the answer and question, the harder, quote-unquote, harder domain is answer. And this is the domain that the agnostic algorithm focuses on to improve. And you'll notice that this is supported by looking at the baseline federated averaging uniform, where a question outperforms answer, significantly outperforms answer. But you'll notice that training only on answers doesn't actually get you as higher performance as training with agnostic. And that might be because, for example, that training only on answers doesn't make good use of the data that's available in questions, in the questions domain. However, when we use the agnostic algorithm, you'll see that it not only improves the accuracy of answer as well as the perplexity, but also decreases the difference in performance between answers and questions. And you'll see that the difference between the 2 is significantly lower when applying the agnostic algorithm as compared to both of the baselines. Our second experiment uses the Spanish virtual keyboard live experiment. So this experiment is a live experiment on millions of actual user devices. And in this case, we're training a language model for virtual keyboard. And there are 3 domains. In this case, there are Spanish locales, ESUS for Spanish speakers in the United States, ESAR for Argentina, and ES419 for a subset of countries as defined by the UN region code for 419. This experiment corresponds to the client partition because each user device falls within a single region or a single locale. And in the table below, we report results. And again, we see sort of similar behavior as we saw last time with the Stack Overflow dataset, where ESAR is shown to be the quote-unquote harder domain, given that it has the worst perplexity out of the 3 domains. And training only on ESAR, while it does improve the ESAR perplexity, it's improved even further by using the agnostic algorithm. And again, this might be because of the agnostic algorithm being able to better make use of the other domain data, or the out-of-domain data, whereas training only on ESCR ignores that additional data. But again, agnostic has the best perplexity as well as the best accuracy for ESCR, which is the domain of interest, out of the three algorithms. Finally, in the graph below, we plot the learning curves for both the Stack Overflow dataset as well as the Spanish experiment, for the domain of interest, which for Stack Overflow is answer, and for Spanish is ESAR. And as I mentioned previously, you'll notice that the agnostic algorithm does converge to a higher point faster as compared to the federated averaging uniform baseline. So this is interesting because this essentially also shows us that in practice, the agnostic algorithm might be able to reduce or effectively eliminate the additional communication overhead required for the domain statistics calculation by being able to converge in fewer amounts of communication rounds. Thank you for listening, and if you have any further questions, feel free to reach out to either me or any of my collaborators. And if you'd like to see more about the work, feel free to read through the paper, and thank you for your time.